Okay, let's begin. Have you seen the topic on the screen? Are you a Newton person or Leibniz person? Okay, so who invented calculus? Perhaps both of them did. Yeah, we cannot go back and check in the past what really happened. But the definition, I hope you remember your calculus course. Yeah, it just happened last year. So, the definitions of limit, continuity, differentiation, integration, they were not as you study them now, back then. So, Leibniz was born in around 1644 and he died in 1717. So, very long time ago, okay. But his definition of continuity is that, it's something very simple which we all understand but which we cannot write down. If 2 points in the domain are really close, then their images are also really close. Very simple definition, that's continuity. But what is the definition that we use right now? We say that for all epsilon greater than 0, there exists a delta greater than 0 such that whenever the difference between x and y is less than delta, then the distance between fx and fy is less than epsilon. So, we had to arrive at this particular definition after some time. So, here the definition that you normally know, that is called hard analysis, because it involves some estimation of parameters. For every epsilon you have to find a delta, suitable delta, okay. Whereas the original definition, which simply states that if 2 points are very close, then their images are very close, there is no estimation involved, it's like soft analysis, okay. And the link between this hard analysis and soft analysis is going to be the theme of today's lecture. Yeah, now we have been talking about calculus. It doesn't feel like a logic lecture at all, but there is lot of logic involved in here. So, let me be very precise with what Leibniz originally intended to say. He said that if 2 points in the domain are infinitesimally close, then their images in the codomain are also infinitesimally close. Okay, that was the original definition. Now, let me write down what is the infinitesimal. Okay, so say that epsilon is an infinitesimal if, well, first of all, its absolute value should be bigger than 0 and the absolute value of epsilon is also smaller than 1 by n for all n in natural numbers. Now, look at this. Yeah, infinitesimal is non-zero, it is positive or negative, and it should be smaller than all 1 by n's. Can there exist a real number satisfying these properties? If you are smaller than 1 by n and you are positive, smaller than 1 by n for all n and you are positive, then what can you conclude? The number is 0, but we are also given it is not 0. So, very soon people realized that, oh, this definition doesn't make sense, because the thing is that infinitesimals do not exist in R. Okay, then this definition was meaningful but also meaningless. What was the definition of continuity? That if, continuity is that continuity of f, let's say from R to R, is for all xy in the domain if mod of x minus y is an infinitesimal then mod of fx minus fy is so too. Okay, so now this definition, the idea was picked up, obviously, because right now that's what we say, for all epsilon greater than 0 there exists a delta greater than 0 such that whenever the difference, you can make the difference between 2 points in the domain as small as possible, and then here it will become as large as possible. Now here we are particularly talking about real numbers, okay. Can you tell me some properties of real numbers? I mean some structures on real numbers. It's an ordered field. Okay, good. Yeah, it's an ordered field. So let me quickly remind you, order is a binary order. We are talking about strict order, let's say. Then field means it has addition, which is associative commutative. It has identity and inverse. Then multiplication is also associative commutative, has identity, it distributes over addition, and most importantly every non-zero real number has a multiplicative inverse. Okay. Now if at all our real numbers were to have infinitesimals which are very very small and close to 0, then their multiplicative inverses should also exist. We want it to be a field. Yeah, multiplicative inverses should exist, and because it's an ordered field, it should be bigger than every natural number. You understand? Yeah, so if infinitesimals do exist, then infinities will also exist. Of course, our real numbers do not have these properties, but for around, so let's say the Newton and Leibniz discovered this in late 17th century. Now until 1950s, people couldn't really figure out the mystery behind this definition of continuity. Okay, how many years? It took around 300 years, okay. For 300 years, nobody could figure out what are these infinitesimals. Because even in definition of differentiation, we also use something similar. Very small change in the value of the function divided by a very small change in the value of the variable. Everywhere the same idea was being used. Later on, people found the hard analytic analogues of that. Okay, so then enters a logician, Abraham Robinson, in 1960s, and he has got many quotes, you can see. Yeah, this idea is not really meaningless. We have to expand our field of real numbers. Okay, so infinitesimals do exist. Infinitesimals and infinities do exist in an extension of R. So our job today is to figure out what this construction is, what this extension is. So one simple thing, yeah, I mean we know what real numbers are. can we try to construct something more complicated from real numbers? So one simple thing is that, let's go to the next slide and let's try R2. How is the addition defined on R2? Component wise addition. What will be 0 for addition? 0, 0. Is this addition associative, commutative? Yes. Can multiplication be defined? Huh? Complex numbers is one possible way, but we also need order. Complex numbers do not have an order relation. So what is the most natural way to define ordering here on pairs? Component wise, yes, component wise ordering. Component wise ordering, component wise multiplication, but there is a big problem. Yeah, so let me point this out to you, that if I take 2, 0 and multiply it by 0, 3, then I will get 0, 0. Are these two elements to begin with 0? So two non-zero elements will multiply to give me a 0 element. So this property is called integral domain. Okay, so this says that not an integral domain. So every field is an integral domain, but well, R2 is not an integral domain, so it cannot be a field, because for example 2, 0 doesn't have a multiplicative inverse. What can it be? Half, what? Infinity? Infinity doesn't exist. Okay, the same problem will persist if I even go to R cube. So let's make our set very, very large. So let's talk about R to the power n. Yes? Min and max can be used to define something, but that will still not give you a field. So yes, I mean your question is really good, so I would like to say something about that. So if with real numbers you take your addition to be min and multiplication to be addition, then multiplication distributes over addition, which means addition distributes over min relation. Okay, if you want some identity for min, what will it be? Additive identity for min. So it should be something like min of x comma something is x. So what should this something be? Larger than everything. It should be plus infinity. Okay, so if I formally add a symbol called plus infinity, I take real numbers union plus infinity, and then I define min and plus as my addition and multiplication, then it is called a tropical semiring. Okay, so tropical because it was invented in Brazil, so that's what Europeans called it. Okay, but it's a semiring. Yeah, the main property it lacks is that it has multiplicative inverse. Okay, multiplication is addition, so addition has inverses, but it lacks additive inverses, because min of x comma something can never be infinity, right? So it lacks the property on addition part. So to answer your question, yes, people call it tropical semi-field, but we don't really want to go there. Yeah, we still want to maintain our usual addition, multiplication, and we want to have less than relation. Yes. 0 into E is 1. What is that E? Once you add some symbol E to this collection of real numbers, then you also have to add its multiplicative inverse. You also have to define how to add those things. So you have to take the field generated by real numbers and your new symbol. Yeah, so yes, it can be done, but right now I don't think you are in the position to understand that. Okay, so now we want to work with this r to the power n, n for natural numbers. So what is this collection of? All sequences, natural number indexed sequences of real numbers. So how do we write an element? A sequence an. Okay, how is the addition defined? Let me write that for you. So addition is defined an n. I mean, I'm not always going to write this, yeah, n in n, okay, plus bn. How is the addition defined? Component wise. So an plus bn, n. How is the multiplication defined? Well, you simply take multiplication here. How is the order relation defined? Order relation an n less than bn n if there exists a capital N, okay, in natural numbers such that
for all small n greater than capital N, bn minus an is greater than 0.
for all small n
Greater than capital N, bn minus an is greater than 0.
So n my
The real numbers bn and n. Yes.
interesting. Why do you come up with this definition rather than the usual component wise?
We saw that. I mean, like if we are considering a sequence, then like this only makes sense, right? Because the sequence is, how do I put it? Like this.
You are on the right track.
This set won't be. Yeah, this works with convergence if we consider that.
This works with convergence. So convergence is on your mind. Okay, fine. I mean, the normal definition would be component wise. Yeah, I mean, this is first option. The second option is that for all n in n, an is less than bn. Component wise, or I mean, let me say less equal, and here let me put less equal. But the problem with this definition is, how do you compare 1 comma 3, yeah, and 3 comma 1? Can these two pairs be compared? I mean, I'm not talking about this particularly, 1 comma 3 and 3 comma 1. They are not elements in Rn, but if you consider them above, yeah, so 1 comma 3 and 3 comma 1 are incomparable with pointwise comparison. So because we are allowing lot of flexibility, yeah, so we are also losing some information. Okay. So the second definition doesn't work because it's not a linear order. Yeah, this is not a linear order. Okay, the first definition still has some merit. Yeah, but we have to now this is interesting. I will give you one particular example. If your definition is that there exists an n such that like eventually you are comparable. The first finitely many terms, you can say they are not really comparable. It doesn't matter. You ignore them. Eventually they are comparable. Now what will happen with this sequence? Okay, tell me with first definition. I am taking 1 0 2 0 3 0 and the second sequence is 0, 1, 0, 2, 0, 3 and so on. Are they comparable? No, they are still not comparable. Yeah, we still have some problem. Although we are understanding something over there. Yeah, the first definition, first attempt is much more valid than the second attempt. We are trying to get closer towards this. Yes. Just one person at a time. Arnav.
So could you give more weightage to the first coordinate? Like, if there are equal, then we just exclude the initial ones which are equal.
Okay, you are suggesting lexicographic ordering? Yes, lexicographic ordering is one way to do this. But we also have the problem, remember, that this is not a field. Yeah, this is not an integral domain. Sujal.
So we can just
Smaller than or equal to? Smaller than or equal to. Like here you are asking me to put this. N is less than capital N. Oh, I mean you are only willing to compare something in the beginning and nothing else matters.
first in the beginning and
Yes.
So do we take norm, like consider we are
Norms of these vectors. In which norm are you talking about? L2 norm is every single sequence in Rn integrable with respect to L2 norm? No. Okay. And this class doesn't know norms yet. Yeah. Fine. So it's not integrable. L infinity will also not work. Yeah. L infinity is supremum. It also won't work. It's not square summable. Not every sequence is square summable, right? So therefore, we still have some problem. So the solution here is an equivalence relation. Okay, so solution is identify some sequences. Okay, now how do we identify? So say that AN is equivalent to BN if the collection of those indices where AN is equal to BN is large. I mean, it should be large, yeah, it shouldn't be something small. Okay, you might say at this point that I have just converted my problem into another language. Yeah, so this collection should be large. The collection of indices where they agree should be large. Now, what is the definition of large? Now, what should be large? Now, let us write down some properties. First of all, do you want empty set to be large? Yeah, because like two sequences do not agree anywhere and then you identify them. That doesn't make sense. So empty set is not large. Do you want the full set to be large? Do you want to identify a sequence with itself? Yes? So N is large. Then if X subset of N is large and X is a subset of Y, then what can you say about Y? Can you see where we are going? Huh? Countable? No. Okay, one final property. If X and Y are large, what can you say about X intersection Y? if x and y are large, then so is x intersection y. Definition of filter. Okay, so voila. Boolean algebras and filters are not leaving us. Okay, one more thing that was a problem here. You observe this 1 0 2 0 3 0 blah 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 and 0 1 0 2 0 3. You couldn't compare them really. That's because this is 0 everywhere except for odd numbers, and that is 0 everywhere except for even numbers. So, well, odd and even, the best thing about them is that they are complements. So, we would like something more to be true, that if a set is large, then its complement is small. So, I am going to add ultrafilter. Okay, so now you probably understand why we defined ultrafilters in a particular way. Ultrafilters capture the notion of large subsets of your given set. Now, okay, one particular type of ultrafilter that we have studied, that is a principal ultrafilter. So, an ultrafilter is principal if all of them share a common element. Yeah, it is generated by an atom in the Boolean algebra. Which Boolean algebra are we talking about? Over here? The power set of natural numbers, okay? So, an ultrafilter on n is an ultrafilter in the Boolean algebra of power set of n. Okay. Now, we still have to go a long way, yeah, to verify that this actually works. Okay. So, I haven't written this last property, but please mention, maybe I should write it down, yeah, so that you will have it on your record, that if x is large, then n minus x is small. Yeah, the complement is small. So, we want ultrafilters. So, let U be an ultrafilter on n, i.e. an ultrafilter in the power set of natural numbers. Say that an is U equivalent to Bn if the set of all indices such that An and Bn agree. This is in U means it is large. So, the idea here is that this is a note. We often want U to be non-principal. Okay, not principal means it doesn't contain any finite set, yeah, i.e. U does not contain any finite set. If it contains a finite set, then it must contain a singleton. I showed that to you, yeah, in the exam answers. There was one mid-sem problem. Okay. So, it cannot contain any finite set, and it has to make decision for every single subset. Odd and even, they are complements. So, either odd is in U or evens are in U. Any questions so far? This is simply a definition, yeah, nothing more is happening yet. Now we have to check lot of things. How do we define addition? How do we define addition of the equivalence classes? Okay, let's write down set star R to be R to the power n modulo this equivalence relation. So, the elements of star R are the equivalence classes of sequences. Okay. So, the set of hyperreal numbers okay, star R is the set of hyperreal numbers. You can actually start with any structure in logic and construct its hyperstructure, but here we are doing it for hyperreal number, yeah, for real numbers. Okay, first things first, addition. What is addition? So, I take an equivalence class of a sequence and I add another equivalence class to it. How should I define it? Equivalence class of the pointwise sum. Okay, so this is an plus bn pointwise and the equivalence class of that. But as is always the problem with equivalence classes, you have to make sure addition is well defined. Huh? Yes, very good. We want that tilde u is a congruence relation. Yeah. Need tilde u is a congruence relation. Okay. So, let us check that. Suppose for addition we are going to check it. Suppose this an is u equivalent to an prime and bn is u equivalent to bn prime. Then we have to check that an plus bn is u equivalent to an plus bn. Okay, an prime plus bn prime. Yeah, we need to check. Okay, an plus bn, the u equivalence class is, sorry, the sequence is u equivalent to an prime plus bn prime. Okay, what does the first condition tell us? That an and an prime are u equivalent. What does that mean? There is a large set over which they agree. So, the collection, so we know that the collection of all those indices such that an equals an prime and the collection of all those indices such that bn equals bn prime, they are both large. This is given. Yeah, this is our assumption that they are both large. Now, what will happen? The collection of all indices where an plus bn will agree with an prime plus bn prime. What can you say about this particular set? This is?
It is at least their union.
it is at least their union. Intersection, not union. Yeah, if two sequences agree, yeah, I mean maybe these things agree somewhere. If this one agrees at 4, an and an prime agrees at 4, but this one doesn't necessarily agree at 4. That can happen. Yeah, so, but can you verify that this contains the intersection? Let me call this x1 and let me call this x2. Then it contains intersection of x1 and x2. See, what I am saying is that if for a particular n, an is equal to an prime and bn is equal to bn prime, both of them happen, then obviously an plus bn is equal to an prime plus bn prime for that particular n. So therefore we know this. Yeah, that the other side is x1 intersection x2 is contained inside this. Now x1 intersection x2, U is an ultrafilter. So therefore x1 intersection x2 must belong to U. And also the second property always, that it is closed under upper bounds. So since this is contained, so this belongs to U and this implies that this belongs to U. Okay. So therefore we actually get that this addition that we have defined here is well defined. Similar thing will work with multiplication. Yeah. So multiplication is also defined pointwise. Okay. Now if we are done with addition and multiplication, I am just going to write down a dot over here and another dot over here, so that addition multiplication is okay. Subtraction, like minus sign, it will work automatically. You don't need to check anything. Now what is remaining? Well, what is 0? What is 0? It is the equivalence class of the constant 0 sequence. In fact, yeah, in fact, there is a natural inclusion from R to star R, which takes X to the constant X sequences equivalence class. Okay. Now something is still remaining. So we have defined addition 0, 1 also can be defined using this process. Now we have to check whether this is actually an integral domain or whether it is a field. How do you check that something is a field or not? Field means every non-zero element should have a multiplicative inverse. Now tell me, how do we check that? What is the meaning of non-zero? Yeah, we need to check that if an, the equivalence class of an, is not equal to the equivalence class of 0, then how to define the inverse? Any ideas?
If it is not 0, then
If it is not 0, then what happens?
there is a small number of 0
Okay, so there is, yes, the set of, this implies that the set of all n's, set of all indices such that an is equal to 0 is small, okay, is small. And then what can you do?
You can replace it with anything else.
Very good. So replace all the entries in this sequence. So let me call this x. Replace all entries in an for n in x by 1, for example, to obtain an prime. Then can you check that this is also, yeah, then the sequence an and the sequence an prime, they are U equivalent. Can you verify this? That these two sequences are, because they only differ by, like, at most they differ on x. They cannot differ anywhere else. Okay. So an and an prime are equivalent, and now every element of an prime is non-zero. Okay, so each entry in an prime is non-zero. So define the inverse of the original sequence to be an prime inverse this sequence . Okay. So now let us go back, yeah, a couple of slides. Look at this 1 0 2 0 3 0. This is non-zero only on evens, odds. Yeah, this is always zeroth location, sorry, evens, yeah. Non-zero on evens, and the other side is non-zero on odds. Now, either the set of even numbers is U large or the set of odd numbers is U large. So one of them is 0. So let's say this is 0. The set of even numbers is large. Yeah, the set of even numbers is large, so I can change the entries, all the even entries, to something else. Oh, sorry, odd entries to something else. Fine. So if let me use green color here. If the set of even numbers belongs to U, then this is not equal to 0. Correct? Because I can change all the odd entries to something else, and then its inverse is, and hence its inverse is what is the inverse, tell me? 1 comma 1 comma half comma 1 comma 1 by 3 comma dot dot dot. You always keep alternate ones. You replaced these zeros with ones, and then you wrote this down, and now you can check its multiplication is 1 almost everywhere. Means almost everywhere means it is equal to 1 on a large set of indices. Whereas this is equal to 0. The second entry is actually 0 because you can change anything in the odd indices. So therefore I can change everything to 0, and this is 0. Do you get this? Yeah, evens and odds, they are complements. So by the last property of ultrafilter, this must happen. Only one thing is remaining now. We have shown that every non-zero element has a multiplicative inverse. We haven't discussed the order relation. Okay. So recall, for addition we just said pointwise. Now for multiplication, for comparison, so say that the class of AN is less equal the class of Bn if the set of all indices such that AN is less equal Bn is large. We actually have to use this. So you don't check for comparison everywhere, you only check it over a large set of indices. Okay. Now we have to check that this is actually a linear order. Okay, why is it reflexive? Why is it reflexive? Is AN less equal AN? Where do they agree? Everywhere. So reflexive because natural numbers are always large. Symmetric, do you need to check anything? Antisymmetry, yeah? Antisymmetry. What is the meaning of antisymmetry? That if AN is less equal Bn and Bn is less equal AN, then you had to use the intersection and an upper bound, same thing. Yeah? So antisymmetry is also done. I want you to write this down, yeah, properly. Transitivity. So maybe AN is less equal Bn and Bn is less equal Cn. So now the set of indices where this inequality is observed and the set of indices where this inequality is observed, you just simply take their intersection and again everything works. Yeah, take intersection and it will be an upper bound. One more thing, that is trichotomy. Well, do it as an exercise. This will work. Yeah, trichotomy will also work. This is actually a linear order. So let us rewind for a moment. We started with real numbers. We wanted infinitesimals. So therefore, we started looking for some higher and higher structures. R square did not work. R to the power n did not work. But R to the power n modulo an equivalence relation, well, that does work. But where are infinitesimals? So now consider the sequence 1 by n. I claim that this is an infinitesimal. Now, can you verify that 1 by n is strictly bigger than the 0 sequence? Yes, because it is bigger than 0 everywhere. Okay, then this is less than 1 over k, constant 1 over k, okay? observe what I am writing. Yeah, 1 over k is the constant sequence indexed by n. Yeah, this is less than this. Is this true? Yes, why? Why is this true for each? Because it's finite? No, I mean, what is the graph of this sequence? Compare the graphs. 1 over n looks like this, and 1 by k is a constant graph. So 1 over n is always going to go below the graph eventually. Yeah?
No,
So-
but we need to show that that's a subset of U, right?
Yes, so 1 over k will always be somewhere like this. Yes, and we need to show this. And how will you do that? All cofinite subsets, I said that often our ultrafilter needs to be non-principal. So assume it is non-principal. Okay, so assume non-principal. So assume U is non-principal, then each cofinite subset is U large, means it is an element of U. And here that is precisely what is happening. Yeah, after some point, a tail of natural numbers will witness this less than. Correct? So we are done. So we got an infinitesimal, and this is also not something that you haven't seen before. Yeah, but it's just that for 300 years nobody saw this. And what is infinity? So the sequence n is infinity. Yeah, so n is infinity. So this branch of analysis and model theory is called non-standard analysis. Okay. So there is a very beautiful blog by Terence Stowe from 2007, Ultrafilters and Ultra Limits, a bridge between soft and hard analysis. Okay, so I recommend you to check it out. So this is non-standard analysis. We have to see something more about this. We are not yet done with non-standard analysis. In tomorrow's lecture, we'll see more. And we will do this construction. This is called an ultra product construction. Yeah, this star R, the way we defined it, we'll do this ultra product construction. Then prove a theorem called Wash's theorem and use that theorem to prove compactness for predicate logic. Yeah, that's our plan. Because ultra products of structures actually provide us with average structures. Statistical averages you are familiar with. So these are model theoretic averages. You are given a bunch of structures and you construct their average structure. It has average properties. Okay, so that will be our way of proving the compactness theorem. Let us stop here.